So in this video, we'll talk about Taylor's theorem, which is the converse of a result that we've seen before. So before we saw that if a function has a Taylor series expansion, then it's holomorphic in that region. Here we're going to see the converse. If it's holomorphic, then it has a Taylor series expansion. Okay, and so that's what we'll do. So if a function's holomorphic, it has a Taylor series expansion. So if f is holomorphic in some region containing an open disk, then f has the usual Taylor series expansion. And here we have a formula for the derivatives. This formula really just verifies a result that we talked about back in chapter 5, namely generalizations of Cauchy's integral formula. So if we have the nth derivative of a function at z naught over n factorial, this works out to 1 over 2 pi I times this integral. So this is the integral of f of w over w minus c naught to the n plus 1 power. Here, r is just some radius that's less than capital R. So remember what's going on here is we're going to do our usual technical trick. We have an open disk of radius capital R. And what we do then is we pick a point in that open disk, and then we find a closed disk of radius little r. The idea with the closed disk is that we get uniform convergence, then everything is nice, everything works out. And since that worked over arbitrary values inside the open disk, then we can generalize from there. So that's the idea. So here we're going to assume f is holomorphic and then derive a Taylor series expansion for f. Now, because f is holomorphic, that means that we can use the Cauchy integral formula, and we can write f of z as 1 over 2 pi I times the integral over this circle. So here I'm going to let c, just for my sanity, I'm going to let c be the circle centered at z naught of radius little r. Okay, so that's this red circle here. Okay, so this red one here, that I'm going to call that c. And this is going to be the integral over c. We're going to have f of w over w minus z dw. So nothing surprising. If f is holomorphic, Cauchy's integral formula applies. Everything is good. Now, what we can do is we can mess with the denominator a little bit. And this is going to be the integral, so this is 1 over 2 pi I times the integral over c of f of w over, what I'm going to do is I'm going to rewrite w minus z as follows. So this is going to be w minus z naught times 1 minus the quantity z minus z naught over w minus z naught. And if you expand, if you just do the algebra, you get that w minus z is this kind of complicated looking denominator here, but it's fine. It turns out to be w minus z. Right? You end up with w minus z naught minus the quantity z minus z naught. So the z naughts cancel, you get w minus z, everything is fine. So that's that. But I'm going to think of this as f of w over w minus z times, so times 1 over 1 minus whatever this quantity is. Okay, and then we can write that as a geometric series. So this is going to be 1 over 2 pi I times the integral over c, f of w over w minus z naught times this geometric series. So this would be the sum as n goes from 0 to infinity of z minus z naught over w minus z naught to the n, and we're integrating with respect to w. And now the key point here is that we had uniform convergence on this circle. There's some technical details here that the book does a better job at explaining, but I just want to give a quick sketch. Notice that this is now a power series in w. W is the variable that we care about, but w is in the denominator. And so if you were to have a power series, if you were to have something like t to the n, as n goes from 0 to infinity, I don't care if t is real or not, this converges if the absolute value or modulus of t is less than 1. On the other hand, if you were to have 1 over t to the n, that still converges when the modulus of 1 over t is less than 1, but that means that the modulus of t must be greater than 1. So now what we've done is, instead of working over a disk, we're thinking of this power series as being valid over the entire complex plane minus a closed disk. So it's going to be valid over some region that's going to look like, we have some z naught here. We're going to be missing this region. Okay, so we're not including that, but then it's going to be valid everywhere else. Okay, and so that's the idea. Okay, so this is going to be valid on that circle. And really all we need to know is that this power series is valid not just on that disk, but actually only on that circle of radius little r. Okay, and so this is going to be valid there. That means that we can interchange the sum and the integral. And this is going to be the sum as n goes from 0 to infinity. Let's see. The sum is just going to involve n. The integral involves w. So I'm going to bring out all the stuff that doesn't involve w. So this is z minus z naught to the n times 1 over 2 pi I times the integral over c of f of w. And then we're going to have w minus z naught to the n in the denominator. So w minus z naught to the n. But actually, that was just this term. We have another w minus z naught here, so that's w minus z naught to the n plus 1. Okay, and so this is going to be what we get. And now, look at what happened. This is our coefficients for the power series. And this happens to be exactly, based on the generalization of Cauchy's integral formula, this happens to be exactly the derivative, the nth derivative of f at z naught over n factorial, right? Because we know that Cauchy's integral formula, we had an n factorial over 2 pi I. Here we're missing that n factorial, so we have to divide by it in the next step, okay? So it's not there. So that's it. That's the proof. So if f is holomorphic, this means that f has a Taylor series.